Good evening and welcome to Specialist Mathematics webinar presented by Texas Instruments Australia. So what do we do in vector calculus? We start with position vector and we need to find velocity vector and acceleration vector. Or given acceleration, like in projectile motion against gravity, and some boundary initial conditions, we can go back to find velocity and the position vector. We are looking at how to find the direction of motion, how to find speed and when the speed is maximum and minimum. There will be questions to show that velocity is perpendicular to acceleration, like in circular motion, or find the times when that happens. And we'll have a look at projectile motion as well. So in 3D space, given the position vector, to find velocity, we need to differentiate each component. And to find acceleration, we find the second derivative or first derivative of velocity. Alternate notation is for velocity r dot in t and for acceleration r2 dots in t. Distance, speed, direction of motion. We talked about distance last webinar. Speed is the magnitude of the velocity vector. So once we have the velocity vector, we need to find its magnitude. And the direction of motion is given by velocity. Velocity is always tangential to the path. So if the question asks for the direction of motion at a given time, you need to find the velocity at this time. So let's have a look at the poll question. We are given the position vector, which has 3 components, and we wish to find the direction of motion when t equals 9. So I will go to the calculator and we'll define our position vector r in t, and we'll use the matrix entry. But this time we have 3 components, so we have to change this to 1 and 3, and we enter what was given in the question. 3 minus t was the I component. So if I move to the next one, it was negative 6 square root 2 square root t. And we jump out of here and move the k component, which was 5. So I have defined now the position vector. If I wish to find the velocity, so let's say my velocity in t will be, and what we need to do, we need to differentiate our position vector. With respect to t of r in t. So it has been done and I can recall it. So this is the velocity vector minus I minus 3 on square root tj, and there is no component because k component it was constant. The question says direction of motion when t is 9. So now if I say v in 9, the direction of motion is minus I minus j, which is answer B, and hopefully you got this answer correct. So let's have a look at question 1 from the handout. This time the position of vector moving in a plane, so we have only 2 components, I and j, is given by this vector equation. We want to find velocity, speed, and acceleration at time 1 and illustrate the situation geometrically. So I will insert a new problem and start with the calculator. And similarly as we did previously, some repetition is good just to remember how things are done. The only difference is that our position vector now only has two components, so I need this 1×2 matrix. So let's enter what was given in the question. It was t cubed for the I component and t squared for the j component. And similarly, I will do the same thing. V in t is the derivative of our position vector r in t. And if I wish to find v in 1 now, because that's what the question is asking, it's 3i plus 2j. So this is the velocity after t equal 1. If we wish to find speed, we need to find norm of, and we can bring this vector down, and it tells us that the speed at this point is equal square root 13. So remember, norm gives us the magnitude of the vector using CAS. Now, the second thing we need to find, the third thing is acceleration. So this time, we might just do the second derivative of the position vector or the first derivative of velocity. Doesn't matter which one we use, we'll get the same thing. So if I wish to see what it is, it's 6ti plus 2j. And similarly, if I want to find the acceleration after 1, is 6 and 2. So what about illustrating it geometrically? Velocity was 3i plus 2j, acceleration 6i plus 2j. So I have that prepared here. So if I just enter the parametric equations, t cubed and t squared, I can see this curve. We've learned how to change to the Cartesian equation, which in this case will be cube root of t squared. So that's our Cartesian curve. And I've selected point 1 and 1 on our Cartesian curve and drew those two vectors, velocity, the vectors 3 and 2, and the acceleration 6 and 2. Notice that if I look at this point, this velocity vector at this point is clearly tangent to the path. And the acceleration vector is always towards the center of the curvature. So it's not circular, but it is a curved path. So that's how we answer question 1. Now moving on to question 2. This time we have the position of an object is given by 3 sine 2ti plus 3 cos 2tj. Those of you who watched our webinar before would recognize that this is a circular path because 3 and 3 and the same angle. So we wish to find the speed at any time t seconds, and we wish to show that the velocity vector is always perpendicular to the acceleration vector. So let's go back to our document, and I will insert a new problem with the calculator. And similarly, we repeat our steps. R in t, and this time we just have two components, 3 sine 2t and 3 cos 2t. And that's done. So velocity at any time, again, will be equal to the derivative with respect to time of our position vector. and I can check what it is. So clearly you could differentiate it yourself. It's not very complicated. So now we want to find speed, but in general, so we know that it is the norm of the velocity vector. And interestingly, speed here does not depend on time. The speed is constant. And as I mentioned, it is a circular motion around the circle, and then the speed, some of you from physics would know, is uniform. But the velocity is not, because it changes the direction. So that's part A. The speed at any time is 6. And now, how do we show that the velocity is always perpendicular to the acceleration vector? So let's start with finding the acceleration vector. So we have this, and we would say we can differentiate our velocity vector and ask the calculator what it is. So now if we compare those two, we note that 6 cos 2t and I minus 6 sin 2tj is the velocity, and that's the acceleration. How do we show that two vectors are perpendicular? We find the dot product. This times that minus 72 cos 2t sin 2t plus 72 of the same thing, which is 0, but we can, of course, do it on a calculator, vector, and if I find dot product of v in t, comma a in t, it tells me that the dot product is 0, which confirms that the velocity is always perpendicular to the acceleration, because our velocity and acceleration are in terms of t in general. Let's move to question 3, which is the question showing this noise 8, which is actually done by a figure skater skating on ice. So we are given the position vector by this equation, and we wish to find velocity and acceleration, the speed after pi on 10, and find the times in one full cycle. So once she completes this 8, at which velocity is perpendicular to the acceleration. So I have already drawn this here, and if we go menu trace, now if you only have CX, not CX2, we'll start with graph trace, and of course you can move around and you will see how it goes. But if you have CX2, we can use trace, path plot, and parametric, and we have this nice animation. So it will just keep on going. So we can see how this skating is happening. Now, because I already have this pre-written here, so if I wish to find the velocity vector, I can do the following thing slightly differently. I will say, let this be equal, and again I have two components there, but this time I will say dt of x1 in t, because I already, as you can see, bold here, I know what x1 in t is. You can see it in the variables because I drew the picture. And I can also repeat this for y1 in t. So my v in t is this formula. Minus 160 sine 20 ti plus 120 sine 10t plus pi on 6j. Remember, you've got to be in radians because we are dealing with circular functions. Now, A in T, we can just differentiate now our velocity vector because we've done that. So that's A in T, and I can display what it is. So this is that I plus this component J. So that's velocity and acceleration of our figure skater. Part B, find the speed after pi on 10. So what I can do, I can find norm of V, and I just put pi on 10, and that tells me that the speed after this time is 60. The last part says find the times in one full cycle when she completes an 8 at which velocity is perpendicular to the acceleration. So of course we need to now think what is the full cycle. So if we look at the equation, we have cos 20 t and sine 10t. So one period is pi on 10, another is pi on 5. You would know that's the smaller period, but if you're not sure, we can say starts at 0, so it's here. What happens if I go pi on 10? Oh, I only get there. What happens if I go pi on 5? Oops, I'm back at the start. So that confirms that one full cycle is pi on 10. Pi on 5, sorry. So what I can do now, I want to find the times at which velocity is perpendicular to the acceleration. So let's find the dot product vector and, sorry, in this view it's sometimes tricky to get it, matrix and vector, and I want dot product number 3, or between velocity, comma, acceleration. So it's a complicated formula. Could I display it a bit better? Yes, I could. If I go to algebra and trigonometry and collect, and if I go up, well, that looks slightly better. Not that we'll be doing it by hand, but remember there is p-collect, and often for speed is quite handy, which I will show you also with the drawn question. So what we want now, we want to solve that for 0. Menu, algebra, solve. And we want this to be equal to 0, t. But of course, it is a trig equation, so we need to give it a domain. So in one full cycle between 0, t, and pi on 5. And we'll do Control Enter here, and that these are all those various times when it will happen. So quite a few of those in one full cycle. What I did previously, I actually saved those as T1 and T2, so I can now check where that occurs. So if I go graph trace and I go T2, that tells me it's here. If I go T1, it tells me there. I only picked up 2 of those, and at those 2 points, the acceleration and velocity are perpendicular. So that answers our last question, last part of question 3. Let's go to question 4, which is the question on projectile motion. So the position vector of a projectile is given by this equation, and the maximum height of the projectile is equal to. So how do we find the maximum height? The maximum height occurs when the J component of velocity is 0. We solve that for time and sub it back into position vector to find where the projectile is height-wise. So let's try this, going back to my document and new problem. And likewise, we'll define our vector, which only has 2 components. And there are, I just need to copy, 15t, that's I component, 29.4t minus 4.9t squared. So if you did any questions on projectile motion, you would recognize this half g here. And now we'll find v in t, as we did previously, by differentiating the position vector with respect to time. And I will see what v in t is. So that's my I component and j component. Now, as I said, we need the j component to be equal to 0. So if I go here, equals 0, and I use this control menu, math section solve. That puts the syntax for me. So I know that the vertical component of the velocity will be 0 after 3 seconds. And now I find r in 3. So it will be 45 horizontally and 44.1 vertically. So if we go back to our question, we see that this is answer E. So that's how we do projectile motion questions. And last question is about a drone. So experimental drone follows this trajectory, but crashes into a wall at time t equals 10. And we assume that distances are in meters and time is in seconds, and we wish to give all answers to 2 decimal places. And this is the series of questions. At what times was the drone flying vertically, horizontally? Calculate the total distance traveled by the drone until it crashes into the wall, and a few other questions. I have prepared that again as the document, and let's see how the motion here happens if we have parametric, and we can see how this drone actually is flying. So somewhere here is flying vertically, and once in the first loop on the top, we'll be flying horizontally, and then it keeps on going, and we'll make another little loop here. On the bottom, we'll be flying horizontally again, and now we can see that when it gets somewhere to this point, it will be flying vertically, as the tangent to the path is vertical. And we go up until it hits the wall. So it hits the wall at t equals 10, and I found this value and drew the wall here. So this is our situation. So let's move to the next one, where I actually prepared it in notes pages. So as previously, if I differentiate x1 and I solve the velocity horizontal component for 0, then I can answer the first question. So if I go here, that is not that good. So we might try just to do Control Enter, because we have to give the answers to 2 decimal places. Similarly, because we already know y1 as I have drawn it, I can solve now the vertical component is equal to 0, and I will do Control Enter again here, and these are the times at which it happens. Now, the next question is asking to find the total distance traveled. So in other words, we are to find the length of arc until it crashes into the wall. So the total distance will be given by the arc length. So again, Vx in t is d dt of x1 in t, and Vy in t is d dt of y1 in t. To find the total length, we need to use the arc formula when we are given parametric equations. So let's try the next question, where we have the speed of the drone at t equals 10. So we can find Vx in 10, Vy in 10, and then if we enter here, we find the speed at t equals 10. Using the norm again. Now, if we wish to find at which angle the drone hits the wall, if we again go back to our picture, it hits the wall here. So if we draw a velocity vector here, which has two components, so that will be the angle between velocity and the wall. So how can we set it up? We can set it up by finding the inverse 10 of horizontal component after 10 over vertical component after 10. Because I'm in radians to draw everything, I need to multiply times 180 by pi to get the angle in degrees. So the angle is 24.89 degrees. This is the angle between the velocity and the vertical. And the last thing we look at is the maximum minimum speed. So again, if I find norm of the velocity, it gives me this equation. Now, if I expand it, it's 10 minus 6 cos t. So we have inside the square root 10 minus 6 cos t. Cos t is between minus 1 and 1. So the maximum is square root 16, which is 4, and the minimum speed is square root 4, which is 2. Velocity perpendicular to acceleration. Again, we need to solve when the dot product is equal to 0, and we get those points 0, pi, 2 pi, and 3 pi. Magnitude of accelerations, once we define the acceleration, interestingly that the acceleration here is constant, so the magnitude of acceleration is constant. I also drew acceleration and velocity at any time and drew both of those in one diagram. So that was our last question for today. So there is a few more questions on the student handout with fully worked solutions, which one I encourage you to solve and check your understanding and how to use the calculator effectively. Thank you for listening.